Okay, here's our next problem. And so what we have is white light that's shining on a vertical soap film. And it's 10 nanometers thick at the top and gets to be 1,000 nanometers thick at the bottom. And the wavelength of the light, it tells you, is 450 nanometers to 700 nanometers. And the index of refraction of the soapy water is 1.33, same as water. So what is asked is to make a drawing of the appropriate drawing to describe the interference pattern, describe how you know which thicknesses are allowed, and find the thickness of the top bands of reflected blue light. Okay, so what I would recommend is just, for me, I actually have to start with a drawing and include all the information that I know. So let's go to a blank page. And excuse me. So we've got a soap film, and we know that the top of this film, and this is not going to be to scale at all, but the top of the film is 10 nanometers thick. So 10 nanometers. We know the white light, which contains many different wavelengths, multiple lambdas, is 450 nanometers to 700 nanometers. And that is going to enter this material from n equals 1, the refractive index of air, to n equals 1.33, the soapy film. Down here, we are expecting this to be 1,000 nanometers. And the question is, what is the interference pattern? How does it form? And what are at what distance, presuming, let's call this x equals 0, the top, from this top, where do we see the first two blue bands? Okay, so first of all, let's just kind of think about what's going on here. We know that any time that a light ray encounters a material with a different refractive index, there will be two things that take place. There will be the light ray coming in. The light will actually reflect off of this, so you have reflection, and you'll have transmission. And then at the next interface, you will also have reflection. Now I'll draw this in a different color. You'll have reflection, R, and then transmission. So again, this ray coming back, you're expecting it to go through a similar sequence where it's going to transmit. This reflected wave is now transmitting through here. Now, since the film is on the order of the wavelength of light, we're expecting the light rays to be coherent when they enter and not coherent when they come back. Okay, so remember that we are viewing the whole thing from this side. So here's the eye over here, and the thing that we see is the combination of the reflected wave and the transmitted wave. One of the things we also have to recall is, how do reflected waves behave when they encounter interface where you're going from a low refractive index to a higher refractive index? Recall that just like a string, if we had a thin string attached to a thick string, like I'll make it sort of obvious like this, a thicker string, that if we were to send a pulse down that string, that at this interface between the thin and thick, you'd get the transmitted wave into the thicker string portion, of course. That would be transmitted. But what you'd also get is you'd get a reflected wave, and the reflected wave would be inverted. That the thin, roughly, think about collisions, that the smaller one would actually absorb the momentum and invert and go that way. In this case, you'd get an inverted wave here on the reflected. This is inverted, so I'm going to indicate inverted. And then at this interface, where you go to higher refractive index to lower, you do not get an inverted wave. So the second reflected wave is not inverted, and it passes through it's transmitted through into the refractive index of 1 without also being inverted. So we have one inversion, and therefore our rules are that you will get let's see, constructive interference. So they will combine constructively when the delta path for the two waves, this wave here and this wave here, which is equal to 2 times the thickness, equals, so you have one inversion. Normally, if there's no inversions, it would be an integer number of wavelengths, but since it's one inversion, you have to add in a half. So this reflected wave is inverted. You have to add a half lambda in order to get constructive combinations of the different colors. So what would the pattern look like? My expectation is that you would first get constructive combinations of the shortest wavelength, since you're starting at the shortest thickness. As you go this way, go downward. And in my mind, you would simply see a kind of a rainbow pattern. You'd see violet, indigo, blue, green, yellow, orange, red, and this pattern would repeat itself as you go down the film because of these thicknesses changing. So that would be this is the interference pattern as viewed from this side.